Hi, I'm Markou, and today I'll talk about sharper convergence rates for non-convex optimization via reduction mappings. This is a joint work with Thalaiyasingam, Ajanthan, and Gould. Modern models are heavily over-parametrized and their objectives have invariances, so instead of a single optimum, we'll get a whole solution manifold. That geometry creates ill conditioning. Some directions are very flat, others very steep, so first-order methods have to take conservative steps and they slow down. This pattern shows up a lot in machine learning, so the natural question is, can we exploit that structure? Our goal is exactly that. Can we systematically use the geometric structure of the solution set to speed up convergence? We do this with what we call reduction mappings. Basically, we reparameterize so that the part of the solution manifold we already know is built in, and we optimize the composed objective, capital F, on that manifold instead of the whole space. But not every reduction helps. The benefit depends on how the structure is incorporated. In over-parameterized problems, we usually see two problematic kinds of directions. One that comes purely from symmetries, which are very flat, and ones that are much more curved than the rest, which are very steep. A well-chosen reduction removes the symmetric induced directions by selecting a canonical representative of the solution, and then the induced geometry rebalances the remaining directions so the steep ones don't dominate. The net effect is a better conditioning problem. In the fingers on the right, you can see this. Each curve corresponds to a different reduction that slices the same ambient landscape differently. We assume we are in an interpolation regime and work near a solution. The original objective is C2 and satisfies a local PL condition near the solution set. We choose a smooth mapping um, whose graph meets the solution set, and we impose a mild alignment condition so the reduction doesn't point us into the worst curvature directions. Under those assumptions, for affine reductions, we can show that the reduced objective becomes smoother, its PL constant improves, and therefore its conditioning number improves. We then extend to these nonlinear cases by adding a bounding distortion condition, so that the curvature introduced by the mapping doesn't undo these gains, and we treat argmin defined reductions in the same framework, which is in the form that often appears in practice. Composing with a reduction induces a pullback metric R of the following form. After reduction, the pure geometry directions are gone, and this metric now reweights the remaining directions, especially the overly steep ones. If we do steepest descent in this metric, we get a geometry-induced preconditioner. And the nice part is, under mild condition, even plain Euclidean gradient descent on the reduced objective is faster than the full one, simply because the reduced problem is better conditioning. Let me show you some synthetic high-dimensional experiments. The first one is a high-dimensional quadratic where we have two coupled variables and we know the exact relation between them. So the reduction enforces that relation and collapses the problem. The second one is the nonlinear version of the same idea where the coupling goes through a tanh type nonlinearity, so the reduction now is nonlinear. We compare three things: gradient descent of the full problem, gradient descent of the reduced problem, and geometry preconditioning version. In the quadratic case, the geometry preconditioning method coincides with Newton's on the reduced objective and essentially jumps to the solution, and even Euclidean gradient descent of the reduced problem improves over the full problem. In the nonlinear case, we see the same process, but now it resembles Gauss-Newton. The geometry-aware version is clearly faster, and even the plain reduced version benefits from the improved conditioning. Outside these least square style settings, we're not doing Newtons or Gauss-Newtons, we only recover them in when the structure matches. So to summarize, over-parameterization and invariances give solution manifolds an awkward local geometry. Reduction mappings let us encode the known part of that geometry, which removes flat and overly steep directions tied to that part. Under mild alignment and distortion conditions, this actually improves the smoothness and PL constants. The pullback metric gives a principal preconditioner, and that in special cases becomes Newton's or Gauss-Newton method. And even plain gradient descent of the reduced problem can be faster than gradient descent of the full problem. You can find the paper on arXiv. Thank you.